everyone, welcome to this lecture number 10 of the NPTEL lecture on charging infrastructure. In present lecture we will see discussions related to single phase boost PFC converter. In the last class or in the last lecture, if you see, we have understood that in the boost PFC case we have full bridge diode rectifier at the first stage followed by a boost converter, which will be used in such a manner that the current drawn from the full bridge is following the same variation as that of the VD, which is actually varying. So we know that VD is varying as modulus of Vs sin omega t, Vs peak sin omega t. So we know that since Vd is varying in the form of rectified DC output, or you can say that modulus of sin omega t. So to do that, since the voltage at the A and B point is fixed, determined by the AC input voltage, we only have a control on the voltage which can be applied from node C and D. So this variation can be done by varying the turn on times of S1 and S2 switch in a way that we will apply, in an average sense, we will apply the voltage which is we have defined here as V converter in such a manner that the current drawn will be following the pattern as that of the VD, which is again having the rectified sine wave variation. So we have seen the functionality of that. Again we have taken certain consideration that the switching frequency of S1 and S2, which is F switching FSW, is very much greater than Fs, which is again supply frequency. So this is 50 Hertz. This one will be somewhere in the tens of kilohertz, maybe 10, 20, 30 kilohertz, depends upon the designers or the circuit designer considerations or the loss considerations, several other aspects one can take while designing this thing. And we have also seen how these different modes of the circuit looks like in a positive half cycle when the D1 and D4 is forward bias, and in one of the switching instance when the duty ratio is defined by the fixed D. We have seen that during the turn on period of S1, we define the turn on period as dTs. During that period of time, the voltage applied across the inductor is modulus of Vs, where Vs modulus of Vs is the magnitude of the input or rectified input at the output in that particular switching instance, in that particular switching period. So in that place, the during the DTS period when the S1 is on, the voltage applied across was modulus Vs. In 1 minus DTS period, the voltage applied was modulus Vs minus V0. Since the V0 value is greater than the Vs peak, we will see why we have to take the V0 value as greater than Vs peak in subsequent slide. So assume if this is the condition, then in that case we have the negative voltage which is applying across the inductor, as a result of which we have a negative slope of current. In the DTS period it is a positive slope of current, in the 1 minus DTS period it is a negative slope of current, and as a result of which this inductor current, which is also same as ID, is having some average value. And if this average value need to be varied in a manner same as that of the VD, then we also need to make sure that this duty need to also vary in some relation as that of the VD which is there. And when it is S1 is turned on, there will be current which will be going through the S1 switch, and when S2 is turned on, the current will be going through the S2 switch. Now along with this, we also know that one of the other important consideration of this converter is we also need to make sure the output voltage V0 is maintained nearly constant or within a permissible limit, or the variation of the output voltage has to be within the permissible limit, that means within some percentage. So in that, because of this particular case, we need to make sure that since the input voltage is varying in the form of modulus of Vs peak sin omega t, we also need to make sure that this duty ratio need to vary in such a manner that we get the constant voltage at its output. So it is important to find out the duty in such a manner that both the things get satisfied. One, we can get the constant output voltage, at the same time the variation of ID is similar as that of the variation of VD. If the variation is same, then we can make sure that we have the constant output voltage along with the unity power factor current drawn from the source. So let us try to see how the duty ratio need to be varied. But before going through that, let us also understand, as I mentioned, that this average current through the inductor is something which is varying in every switching cycle. So if you try to draw, let me draw the current in this manner. So let me first draw the VD, which looks like, let me take slightly deeper this thing. Let me take the VD. So our VD will be having something like this variation, and if we take one more cycle, we can say that our VD will be varying this way. Now let me define this as VD. Since our VD is varying in this way, we also want that our inductor current must be also having some variation as that of VD, which is to have the unity power factor. So assume our inductor current on an average sense will have a variation drawn all over here like this. So let me mark it a certain thing. So now if we look very carefully, since the average variation is obviously, it looks like in a one switching period it will always be a single value, that average variation, and that particular average variation will be varying with the modulus of sin omega t as shown over here. So thus along with that, the actual current which is going through that will have some ripple as shown over here. So similarly you will be seeing that the actual current, IL current, will be look somewhere like this. And same thing will follow in the next cycle as well. So starting, the S1 will be switched on for more time, then S1 will switch on for less time, and as a result of which you will see the variation will look like this. Something like this. So this is your actual IL current or ID current. Let me draw this as ID, and your this dotted one is the ID average, which is actually average value will be following the same pattern as the VD is following, and thus as a result of which you will be in a position to have the same variation of the current in an average sense as that of the VD variation, and thus we can ensure that there will be unity power factor current drawn from the source. So here if you look very carefully, if we increase the switching frequency, that means we reduce this time period which is Ts. If we reduce this time period, then we will be ensuring that the current will be looking nearly sinusoidal. Obviously there will be a small ripple over that average value which will always be there, so that we can ensure. That's why the Ts also has to be very much smaller than our T value, or you can say that, in other words, we can say that F switching has to be very much greater than Fs value. So that will also give you the consideration which we have taken, that Fs switching has to be very much greater than the supply frequency. That also tells that the consideration what we have taken gives a much better result. Further, along with this, since if you look very carefully, as the average value changes, the pattern, the ripple pattern also changes, the current or the actual current pattern, that means for some time positive slope and then negative slope, that pattern will also change. That means the time for which the positive slope is there and time for which the negative slope is there is also varies, such that the average current will need to vary similar as that of the VD. So thus must ensure that the portion of the time during which S1 is on and the portion of the time during which S2 is on also need to be vary with respect to the time. So thus let us see how we will get the variation of the turn on times of S1 and S2. So for that let us try to derive that particular relationship of how the duty ratio changes in order to get the DC link voltage, which is constant DC voltage V naught, along with current drawn from the source is having the same variation as that of the voltage, and that means we will get the unity power factor operation. So let us try to derive the variation of the duty ratio with respect to time. So let us take the waveform which we have drawn in the previous slide, the same variation. If you look very carefully in this particular case, let me, this is your nothing but your VD voltage which is been applied from the input. Since the VD voltage is varying, however our output voltage is nearly constant. If you see the circuit, the output voltage is nearly constant, and I mean within, obviously the variation is within the permissible limit, but still the voltage is nearly need to be regulated at a nearly constant voltage. So let us see how we can calculate the duty ratio. If you recall, in our normal DC-DC converters, we used to calculate the duty ratio by doing the volt second balance across the inductor. In this particular case, this is the inductor in the boost part of that boost PFC. But if you look here very carefully, the average value of current, or you can say the whatever the average we have, is keep on varying in every switching cycle. It starts from 0, it reaches to the peak value, and then it goes down to 0 again. So the volt second balance which we apply will not hold, which we used to apply for every switching cycle, will not hold true. However, we have to do the volt second balance for the entire half cycle, or you can say that for entire T/2 period. This is for entire T/2 period, because in T/2 period the average value of the current which is going through the inductor, the ID is nothing but the IL. So the average value of this inductor current will be started from 0, goes to its value, and then goes down to 0. So we have to do, and since the current is going in that way, that means the flux will also be varied in the same manner. So thus we need to make sure the volt second balance in the entire half cycle will need to must become 0. So thus if we assume, if assume d of t is the duty ratio, which is saying which can be said that the fraction of the time of the switching period in which the switch S1 is on is the duty ratio that is varying with time. And let us also take the Vs of t, or modulus of Vs of t, because this is the voltage which will be applied at one end of the inductor. We have seen here this modulus of Vs of t, here it is applying Vd at this point. Let us see how the volt second balance will look like. Let us say in one switching cycle we are applying for dTs period. We have seen that for dTs period we are applying the voltage of modulus Vs of t, and in 1 minus dTs period of time we are applying modulus Vs minus V naught voltage across this inductor. So we can write down that modulus Vs of t applied for dt of Ts period, plus we can write that Vs of t minus V naught voltage applied for the period of 1 minus dt of Ts duration. This particular volt second which is there in one switching cycle, we cannot make this particular volt second to be equal to 0, as the starting point and the ending point of inductor current is not same. However, since the average value is keep on growing till peak and then goes to 0 at the end of half cycle of the input AC voltage, so we can then add this volt second in each switching cycle over the half cycle of input AC voltage and then make it equal to 0. So we can do in a continuous form, we can write the variation goes from 0 to t by 2 becomes equal to 0. However, this integration is difficult to solve, but since we have assumed that f switching is very much greater than Fs, which means that the step change in the average value of current in a switching period is very small. Thus, we can approximately say that the starting and ending value of inductor current in a switching cycle is nearly same. This will give rise to a condition which is modulus of Vs d of t Ts plus modulus of Vs t 1 minus Ts period is equals to 0. That implies if we rearrange this thing, we will get modulus of Vs of t d of t minus V of that implies so Vs t dt plus modulus of Vs of t minus V naught minus modulus of V of t dt minus become plus V naught d of t equal to 0. These two get cancelled out. That implies Vs modulus of Vs of t is nothing but this, we can go there, V naught 1 minus d of t, and that we can rearrange this thing and we get that the variation of dt is nothing but 1 minus Vs of t divided by V naught, and we can write this particular expression as d of t is equals to 1 minus S peak sin omega t by V naught. Now if you look very carefully in this particular expression, which is, let me again write that expression. In this particular expression, if V naught is greater than Vs peak, so at the extreme case when sin omega t is equals to 1 and I make sure at that point if V naught is greater than Vs peak, then I am 100% sure that the d of t is always between 1 and 0, and this d of t is some positive quantity. Now if the V naught is less than Vs of peak, the d of t is less than 0, or you can say the negative value, and this is not at all possible as the d of t is nothing but the fraction of the time during which the S1 switch is on, and the time can never go negative. That is why this particular condition is not at all possible. Thus, with this converter with boost PFC converter, always the output DC voltage which you get will always be greater than Vs of peak. Now let us say if we consider 230 volt RMS, then the peak will be 325, and that implies my V naught has to be greater than 325 volt. Generally people take V naught is equals to 400 volt, also to take care the different voltage drops across the devices and the inductor. So that is why always, that is why the name also suggests the boost converter, and also it actually boosts the voltage which is appearing at its input, which is nothing but the VD voltage which goes between 0 to Vs peak again to 0. So thus the output voltage has to be greater than that. Now if we look very carefully in this particular thing, let us see how this particular variation look like. Obviously with respect to t, let me first draw for one cycle. So in one half cycle, if my Vs goes from 0 to Vs, VD goes from 0 to Vs peak and coming back to 0. This particular value, let us define as this Vs peak, and this is variation is nothing but VD. It is varying like this. Again in the next cycle also we have the same variation, and this is nothing but going maximum up to Vs peak, and our V naught will be somewhere here. Some room is there, V naught, what we are getting. So thus our duty ratio will be varying from, define this as value 1, because duty is between 0 and 1. It goes from this value, it is just opposite of this particular variation will also be going like this. So this particular thing we can d of t, and this particular value which is there, this particular value is nothing but 1 minus Vs peak by V naught. This particular value which is nothing but 1 minus Vs peak, which happens at the place where we have the Vs voltage, which Vd voltage reaches to its peak value. Further, we can see that how our current will look like. So let me draw the current. So since our this duty ratio is varying in this particular manner, it is just the 1 minus Vs of t divided by V naught, then we will also see that our average value of current will also be varying similar to that of Vd, along with maintaining the same phase between the current and the Vd voltage, and that will be reflected, or that will be actually will be unfolded, and the same current will be drawn from the source. So this is how we can ensure that two things we can ensure: the variation of the output voltage is constant, at the same time we ensure that our ID current will also be following this the pattern as that of the VD, along with maintaining the same phase between them. So let us see now. So we understood how the system work. So this is the duty ratio which has to be varied for the S1 switch in such a manner that we will be in a position to do that required operation. That means the time, or the time for which this S1 switch need to be on, and the remaining of the switching period the S2 will be on. So let us see, let us go ahead and try to do the sizing of different component in the boost PFC converter. So let us go ahead and see. So since we have calculated this duty ratio value of the time during which which indicates the fraction of the time during which the S1 switch is on in a switching period. Now let us try to define different sizes. Let us try to size different component of this boost PFC converter. So if you look the boost PFC converter, what all components we have to size? We have to size this inductor, we have to appropriately size this capacitor, we have to appropriately size this S1 and S2 switch, we have to appropriately size this D1, D2, D4, D3, D4 diodes, and obviously this RL will be defined by the load specification. Also this the output DC voltage will be determined by the specification of this converter. So thus let us try to size this particular components. So let us first try to focus on sizing the inductance L. Now while sizing the inductance L, let us recall how our inductor current looks like if we see the waveform. So inductor current will be having the positive slope in dTs period and it will have the negative slope during the 1 minus dTs period, and the current is varying between IL max and IL min value. So let us define one term called as the delta IL, which is nothing but IL max minus IL min. That means current has to go from the minimum value to the maximum value and then coming back. After defining this delta IL term, let us see during d of t Ts period, we know that the voltage applied across inductor is nothing but modulus of Vs of t, as we have also shown over here. Voltage applied is modulus Vs, which is nothing but the values which is coming over here. So during that time we can write as modulus of Vs is nothing but L di, which goes from, during this time it goes from some minimum value to the maximum value. So we can say delta IL, and the time during which it goes is during d1 dTs period. Now that we can rearrange and we can write dTs period Vs of t. Now this we can define it as equation number 1. Similarly, during 1 minus dTs period, the slope is negative and the voltage applied across inductor is modulus Vs of t minus V naught, and that will be minus L delta IL by 1 minus d of t Ts, and that we can rearrange this particular term. We will get the 1 minus d of t Ts. We can write delta IL divided by V naught minus Vs of t. This, let us define this as equation number 2. Now add equation number 1 and equation number 2, that will give you Ts, because 1 minus d and dt will cancel. Ts is nothing but L delta IL t plus L delta IL naught minus modulus of Vs of t. Here we have taken one assumption that the starting and ending value of inductor current in a switching cycle is same, which holds true as we have taken F switching very much greater than Fs. So now let us see how the overall system look like. Overall, I mean, when we will try to solve this particular expression. Before that, let me also assume the IL goes from IL min to IL max and then coming back to IL min. That is the assumption we have taken. So if we rearrange this particular expression, what we will get is del IL, let us take it outside. This will be modulus Vs of t by V naught minus modulus of Vs of t, and this will be V of t plus Vs of t modulus. Now this and this will get cancelled. Delta IL by Vs of t Now this particular expression I can write as, also I can rearrange this particular expression and I can write in a simpler manner. I can also write this, I can rearrange and I can also write Ts is nothing but 1 by Fsw, so that I can write that delta IL is nothing but V naught minus Vs divided by L W. Okay, here I have missed one V naught term, this will also go here V naught. Now using this expression we can obtain or we can get the delta IL value, maximum value of delta IL value by differentiating the delta IL with respect to modulus of Vs of t and make it equal to 0. That particular thing will lead to, this particular expression will lead to d of d modulus of Vs of t minus equal to 0. That implies V naught minus 2 Vs of t modulus equal to 0. That implies my modulus of Vs of delta is equals to V naught by 2. So this indicates that this ripple IL becomes maximum when the input AC voltage and the input AC voltage or the VD value is equal to the V naught by 2. So thus we put this expression, let us say this one as 3 and this one as 4, put or substitute 4 in 3. So we will get expression, we can write down that delta IL max is equals to V naught minus V naught by 2, and this one also we can write down V naught by 2 divided by L Fsw V naught. Now that particular thing will come down to value as V naught divided by 4 L Fsw. Now in this particular expression we can again rearrange and we can get L value as V naught divided by 4 delta IL max times F switching frequency. So we can see that this is the value of inductance one need to have. Now here if you look very carefully, when you define the specification of the converter, already you can define this V naught value. So this V naught value is defined. F switching is the designer choice depending upon the losses and depending upon the functionality and EMI performance. One can select the F switching frequency one can select the switching frequency of S1 and S2. However, one need to ensure that this switching frequency has to be very much larger than the supply frequency. At the same time, one can also define in the the designer can also define, or it could also be there in the specification, that what could be the maximum allowable ripple through the inductor. Now generally this ripple, generally they take this delta IL max is generally less than or generally less than 10% of IS peak, which is peak value of the current drawn from the source. Generally this particular things is been taken, designer can also take 5%, 2%, accordingly their L value is decided, and then they can actually size their, or you can actually design their inductor to obtain or to achieve that particular inductance value. So thank you for listening to this particular lecture where we discussed how the duty ratios or how the turn on time of the switches in the boost PFC converter need to vary. And also we have started doing the sizing of the component, so we have understood or we have calculated the value of the inductance L. Now in the subsequent lectures we will design the capacitance value and see the different RMS currents of these switches and also the voltage rating of the switches. So thus with that one can easily size the boost PFC converter, and then we will see the controlling or how to do the control of output DC link voltage along with the ensuring that the current drawn from the grid is having the unity power factor variation. So thank you for patiently listening to this lecture.